Good morning and welcome back. Let's continue our discussion about chapter 6. We still have maybe page 71 to 83, not too much, the last part of chapter 3. Last time we talked about electric field here. Change to pointer. Okay, we talk about electric field propagate in K direction, perpendicular to the magnetic field. In that case, we will have a K just in the perpendicular direction. And electric field in Kx and Y direction, S direction and Y direction. So electric field in this plane and wave propagating in this plane. So it's not an ideal plane wave. For ideal plane wave, K will perpendicular to E1. That's plane wave. So this is not a plane wave. Not a plane wave, doesn't matter. It's still EM wave from my viewpoint. So, okay, so let's move on to the next page. Nicholson tells us under this condition, we have a extraordinary mode. Okay, let me change to here. Then use laser pointer. Okay, use mouse. Nicholson checked section 7.9 for fluid treatment. We will deal with extraordinary mode, starting from the very similar equation 239. Let's have a look at 239. Okay, this one. That's the determinant 239. So from 239, this mode is actually very special, very strange. Therefore, we give it a name. At high frequency, we may negative the ion contribution. Then 239 can be written as this one. Just consider electron contribution, because at higher frequency, ion contribution is very small. The ion contribution, very small. Whereas before, electron sectron frequency. So we have this relation, this one times this one minus this one. Therefore, I minus. Okay, so we have a minus sign here. That's extraordinary mode. After some algebra, this equation 244 can be written as K perpendicular to here or here. That's identical to 7.178. So we call this one as upper hybrid frequency. Upper hybrid frequency. We just give it a name. This one defined it as upper hybrid frequency. So what happened? When omega is very close to the upper hybrid frequency, then the denominator will become very small and K perpendicular will become very large. Okay, look at another slide. Next slide. This is the this is the dispersion relation for the extraordinary mode it has two branches with the following limiting frequency. For the extraordinary mode, K perpendicular equals 0. So we have two frequencies. Omega 1 here. Omega 2 here. We have two frequencies. Omega 1 and omega 2. Omega 2. So, and equals plasma frequency square plus omega E square over 4 minus plus omega E over 2. Okay, so let's tell us what happened here. Another is K perpendicular equals infinity, which have two solutions. Omega UH, omega, when omega approach omega UH, and the other is another extreme. Go back to previous case. That is omega very large. Therefore, omega square cancel. Omega very large. Therefore, omega square equals another extreme. Okay. For omega very, very large. Okay, let's move on. So we need the left-hand side, omega 1, omega 2. And we also know what happened here. So this is the ordinary mode we already learned before. And these two new are extraordinary. Extraordinary. Thus, as shown in the figure, the frequency of the lower branch goes from omega 1 to omega UH, upper hybrid mode. And the frequency of the upper branch goes from W2 to infinity. Note that at omega equals omega UH, we have dxx equals 0. Hence, E1 equals E1 EX, and the wave is electrostatic. Interesting. Here, look at here. Okay. Actually, these two curves are very close to each other. And a wave becomes electrostatics, called upper hybrid resonance. Upper hybrid resonance. Okay. As omega approach infinity, we have dx as another case. Go back. We have dxx, another extreme. EY equals E1Y EY, and the wave is electromagnetic. Okay, so this one will become electromagnetic when omega very large, and this one will become electrostatic wave. Very interesting. Let me show you another interesting wave. Magnetosonic wave. Magnetosonic wave. 磁声波 Magnetosonic wave. dxs, dxy, dys, dyy equals this one. The same, okay? At low frequency, omega is very, very small, much smaller than ion spectrum frequency. Ion plays a major role. And we must return the ion term. Retain 保留 the ion term under the condition. We must retain the ion terms. So dxx here, in addition to electron term, we must retain the ion term. Okay? Retain the ion term. So since dxx equals dss times dxyy equals 0, we have this one. dyy equals 0 has the same form as a blast of orphan wave. Orphan wave, and this is the orphan speed. Orphan wave. The solution is simply 221 with kz changed to k perpendicular. So very similar to orphan wave with kz changed to k perpendicular. Equation 248 gives the dispersion relation for the magnetosonic wave. Magnetosonic wave, because very similar to orphan wave. It has the electric field E1 equals E1 EY, hence K dot E1 equals 0, and the wave is electromagnetic with B1 in, so one in B1 in Z direction, E1 in Y direction, and the wave is propagating in X direction. Looks like a plane wave. So this, this relation is correct. And K dot B1 is also 0. A physical picture, like the low frequency orphan wave. The particle dynamics can be described by two types of drift motion. First is E1 cross B0 drift, move the plasma in the X, in the S direction. And since E1 is oscillating in S direction, also vary with E1, but polarized in the Y direction. Also varies with X. The drift motion will compress and decompress the plasma, resulting in a density variation along the S direction. On the other hand, the wave magnetic field B1, when superposed with B0EX, will cause similar density variation. Similar density variation of the magnetic field lines, such as this one. It has variation with X, variation with X, and B1 plus B0. The field lines are, again, frozen to the plasma, similar to the orphan wave. The field lines are, again, frozen to the plasma, similar to the orphan wave. Okay, so magnetosonic wave is very similar in many properties. However, the restoring force, thus the oscillation mechanism, is now provided by the magnetic pressure force density, this one. As in the orphan wave, there is also a polarization drift current in the Y direction due to the time variation of E1, EY. This current generates the wave magnetic field, hence the magnetic pressure. Okay. You can derive by using a different approach from fluid equation, chapter 7, which gives the same dispersion relations. same dispersion relation, but much shorter, just one page. Okay, let's consider the asymptotic behavior. Asymptotic behavior of the magnetosonic wave dispersion relations. Asymptotic, which means at the extreme. The dispersion relation for the magnetosonic wave is valid under the condition. Very, very low magnetic field, very, very low frequency. It breaks down as K perpendicular becomes infinity. To find the behavior, this one, we assume omega is greater than this one, unlike this condition. But and omega square is less than, which means omega square is somewhere between ion cyclotron frequency and electron cyclotron frequency, somewhere in the between. So dxx equals this one, okay? So the determinant is still 0. We found that K perpendicular into infinity, but omega remain finite. So we have this equation, which implies E1 equals E1x, EX. The wave is, once again, electrostatic. Okay, so we have electrostatic. At low frequency, we will encounter ion cyclotron frequency. But at higher frequency, we don't have to worry. Electrons' contribution is more important. And the polarization are very important. So it will result in electrostatic but we do not have a chance to deal with magnetostatics. You can study by yourself. Okay, actually, I do not have experience to deal with magnetostatic wave. Okay, so now let's rewrite the equation. Another extreme. Omega is greater than, plasma frequency is greater if under this condition, omega square equals, that's another one. Let's call lower hybrid frequency. So we have extraordinary mode and upper hybrid frequency. And under another condition, we have magnetosonic wave, and which related with lower hybrid frequency. This justifies the assumption omega is somewhere between electron cyclotron frequency, ion cyclotron frequency. Finally, all the perpendicular modes discussed so far are summarized in the figure. Perpendicular mode. 2 is extraordinary, 1 ordinary, together with magnetosonic wave. Okay, so let's discuss. Discussion is normally very important. We have covered a number of most famous. 我们已经覆盖，我们已经讨论 a number of the most famous Fermionian modes. The most Fermionian modes in uniform plasma. 在均匀电浆里面大部分的模式 in the framework of kinetic theory. Vlasov equation. 那记得 Vlasov equation 我们虽然已经讲过，但是我们同时也提到 Chapter 7 Nicholson 的 Fluid Theory， 通常比较容易推导，因为你不需要考虑到 particle 的 behavior、thermal behavior. However, some other Fermionian treatment, Fermionian uniform plasma modes have been left off, 被遗漏了。For example, Bernstein modes. If you are interested in Bernstein mode, you can study by yourself. Section Crow and triple piece. Section 8.12.3. Second, we have only considered wave either alone or perpendicular to the magnetic field. Two cases. In practice, wave can exist at any angle to B0 with complicated expression and mixed properties. The general dispersion relations can be the basis for a detailed study of such uncovered uniform plasma mode. Okay? Third, there are also modes which are not contained in equation 146. 没有包含哦。For example, an inhomogeneous distribution in the density or temperature-induced new mode, such as drift waves. You can also study Nicholson and Crow and triple piece. Plasma in some devices are further complicated by a complex magnetic field configurations, such as plasma. Where is the pointer? Such plasma are usually the subject of research paper. For example, such plasmas are usually the subjects of research paper. Such plasma are usually the subjects of research paper. For example, inside a waveguide, the EM field is actually not uniform. EM field must satisfy the waveguide relations. And inside the charged particle is not uniformly distributed. The magnetic field have spatial orientation. So in a real configuration, real device, the plasma are quite complicated, quite difficult to answer. Most considered in section 6.12 are for a cold plasma. No thermal distribution. Basic properties and the underlying physics are more clearly exhibited in this limit. Cold mode are stable because there is no free energy to drive an instability. 根本没有多余的能量啊。In the next topic, we will demonstrate how a mode can become unstable. Instability in an anisotropic plasma. Stable, which means do not change in time. Unstable, which means it will change in time. Exponential growing or exponential decay. Normally, we refer to exponential growing. That means unstable. Relativistic Vlasov equation can be derived by the same steps as in the derivation of Laplace equation in the section 6.1. For the case we consider the same. The relativistic factor gamma is a constant of the motion in a zero-order orbit equation. Hence, the derivation of the relativistic dispersion relations take exactly the same step which lead to, in the special topics revision next week. Special topics 1, we will derive the relativistic velocity equation and consider a relativistic instability. A relativistic instability. Okay, that will be very interesting. Now, let's focus on a slow wave instability. Instability is very, very interesting. It's a very important issue on the electron-cyclotron method, electron-cyclotron waves. The dispersion relation for the right circularly polarized wave is shown here. That's the dispersion relation. At higher frequency, we may negate the ion. For a cold plasma, it reduced to this one. Okay, we already know that. That's the right-hand circularly polarized wave. Give the two circularly polarized branch in the figures. This one and this one. Two circularly polarized wave. Two right circularly polarized branches in the figure. Below, we will show that the electron-cyclotron wave portion here of the lower branch can be destable or unstable by an isotropic in the velocity distribution, results in a velocity space instability, 速度空间的不稳定性。Okay, due to this case, electron-cyclotron wave. Okay, for an isotropic plasma,不均相的, we cannot use equation 214, but must go back to 203. Again, assume high frequency and negate the ion. Okay, so we have 250. The integral I can be written in this form. Just have a picture. And now let's assume the electron has perpendicular velocity and Vz velocity is 0. So do not move in the z direction. And perpendicular, we have velocity. So it just perform cyclotron motion, which represent a uniform distribution of electron in random phase gyrational motion and velocity here for all electrons. Okay, let's see what will happen. Let's substitute this one to here, okay, and see what will happen. Okay, then I becomes here. That's the new I. Substituting 252 into 250, we got this one. Okay, which reduced to 214 as the two right circularly polarized branch are plotted here. The first one, second. And for this condition, we plot under this condition. The top figure plots omega r as kz, omega r resonance frequency, real part, as function of kz, normalized with plasma frequency. The upper branch is a phase wave. 这个是 phase wave. What is phase wave? That means omega r over kz is greater than the speed of light. That's phase wave. If omega r phase velocity is less than the speed of light, that's slow wave. Okay, as shown here. The lower branch is slow wave. The bottom figure plus omega I versus kz. Omega I, which is imaginary part of omega. So the frequency of omega r plus I omega I, we see that the slow wave is destabilized by the gyrational particle. So omega will have real part and imaginary part. Real part is drawn here, but imaginary part is shown here. It's not zero, which means which feed energy to the wave through spectrum resonance. That means this system is unstable. That's a good news, because from this one, we will observe some new phenomena. The wave will grow in time. So that's why it's instability. That's the growth rate, not a decay rate, but growth rate. Interestingly, what happened to the phase wave? Is there any growth rate in this region? Yeah, that's very interesting. If we have growth rate in this region, that will give us some new information. So we will study relativistic Blasov equation. Under that condition, I will show you, yes, phase wave also has instabilities that is related to electron spectrum measure. We will talk about relativistic electron spectrum measure. That is special topic 1 next week. Okay, that's the end. See you next time.